Hello, this is the second in a series of screencasts on the subject of redox chemistry for the module CHE10063. Okay, so today what we're going to talk about is redox reactions and more specifically about how we represent redox reactions, okay? With the view to next screencast when we're actually going to start making predictions about them. The reading for today is all from Inorganic Chemistry and it's page 187, and that pretty much covers it, although there is also an example on page 1882. Okay, so let's start with what we know about redox reactions. Well, we know that the process of a redox reaction requires electron transfer. It requires something to be oxidized and something to be reduced by definition. So, for example, we've got this reaction here of acid, my H plus reacting with zinc solid, and there's clearly a change in the oxidation state, both of H, which is gaining an electron, isn't it, and zinc, which is losing an electron. So we can already start to identify our species that's being oxidized. So the species that's losing an electron is being oxidized, so that would be zinc. So that's the oxidized version, is zinc 2 plus. And the species that is being reduced is, of course, therefore going to be H plus, because reduction is gain. Yeah, so gain of electrons, meaning H plus goes to H2. Yeah. Okay, so that we can start saying that, and we can say that the reducing agent, which is the species that's oxidized, is zinc. So I'm going to start writing this in actually. So this is oxidized. So zinc is the reducing agent. Okay. And likewise, we can say the oxidizing agent is 2H plus, and that H2 is H plus to H2, H plus is being reduced. So this is the reduced version. Right, when we come to actually look at redox chemistry though, we need to think about how we're going to do this. And the way we need to analyze redox chemistry is we need to split this reaction equation here into two half reactions. And we've kind of already done that. I've kind of already talked you through that, but let's do that in a more explicit manner. Okay, so let's do this. We've already said that H plus is being reduced, so we can write 2H plus AQ plus 2E minus goes to H2 gas. Okay, so we've explicitly put in the electrons here. Okay, so if we've got two moles of H plus, we need 2 moles of electrons in order to get our hydrogen molecule. Yeah. Okay, so this is all balanced, and a key point is that we keep the state symbols in for the species because we want to know where they are, but the electrons don't have state symbols. So electrons don't have state symbols. Why is that? Well, that's because electrons don't really have a state. I mean, we couldn't put electrons 8q because an electron is not going to be stable for any time at all in an aqueous environment. So we don't have state symbols. So I'm just going to write that down here. So species have state symbols. Electrons don't. And that's because electrons, aren't stable in those solution in a solution. Okay, we can do the same thing for zinc. So we just write the other half equation, which is, of course, zinc solid goes to zinc 2 plus, and this is now 2 electrons. So we can clearly see that our 2 electrons are coming from the zinc and going to the hydrogen. Okay, so that's a nice balanced process already, so we don't need to do anything else with that if we're going to recombine them. We'll talk about recombining them in a minute. Okay, now, so we've got these 2 equations, but we haven't quite finished, because convention states that when we're writing half equations, we always have to write them as reduction processes. Now, that's fine for the hydrogen version because H plus is being reduced, so this is written as a reduction already, so that's fine. But for the zinc version, on the right hand side, that's not written as a reduction. At the moment, that's written as an oxidation because the electrons are on the right. So actually, when we're writing the 2 half equations, we need to flip the equation. Okay, so in this case, instead of writing the one we've got, we need to write it actually as Zn2 plus plus 2E minus goes to Zn. Okay, and put a solid in there. And again, no state symbols on the electron, state symbols on the species. Okay, that's just a convention, and you'll see why we do that sort of soon, a bit later in the screencast to some degree, but actually far more when we actually start making predictions with these. You'll see why it is we write them as reduction processes. Okay. Final point on this in terms of convention is that we can write these couples, we can write these kind of equations out as redox couples. So a redox couple is where you have the oxidized species on the left and the reduced species on the right. So for example, for the zinc version, we've got zinc 2 plus / zinc. Or for the water example, you've got, for the hydrogen example, you've got H plus / H2. Okay, and that's another way of doing that. So if you see this H plus / H2, this means H plus, well, 2H plus 2E minus goes to H2, and we can put in the state symbols. And ideally, you'd include state symbols in the redox couple as well. But we've not got them here, but they are there. Okay, so those two things are entirely equivalent. Okay, so that's just an aside. Right, so we both need to be able to break a full equation down into its two halves, but also we need to be able to put two half equations and create that into a full equation. Okay, and actually this bit where we take two half equations and we make a full reaction equation from them is actually the thing that we're going to use a lot when we're trying to do predictions, because typically speaking, when you're doing redox chemistry, you want to look at a table of chemical potentials, electropotentials, and from that you want to say, well, okay, this reaction will work or this reaction won't work, and then you can build the actual reaction from the half equations that are in the table. Okay, so this is the really important thing we need to be able to do. Okay, so we're going to keep on our example of our zinc dissolving in acid, so we know what the final equation is, of course, and it's written on the previous slide, but I want to go through the process of how we go from the half equations that we start off with back to the other one. Now we start with our equations written in a reduced form. Okay, so don't remember that. Don't forget that, sorry. Don't remember that. Yeah, and we've got but we know in our equation that zinc is going to be oxidized and H plus is reduced, and obviously this is going to come from the prediction side of things. I'm just going to rub that out because that's not written correctly. So this idea of knowing which one's going to be oxidized and which one's going to be reduced is going to come from this E cell that we'll meet next time. Okay, I'll just mention now. Okay, so again, these are both written in reduced form, so we need to be able to put one back. But we know that this one's going to be oxidized, so we know that this one's going to need to be flipped. Okay, so essentially what we have to do is we have to subtract the two equations. Okay, so what we do is we say the one that's going to be reduced minus the one that's going to be oxidized. Okay. So the one we're going to be reduced is like this, 2H plus AQ plus 2E minus, and we'll put a big an arrow there, H2, so that's fine, that's written the right way around. Okay, and the one that's going to be oxidized, well, we need to put the stuff on the right hand side of the half equation, that needs to go on the left hand side here, doesn't it? So we're going to have to put plus Zn S, so essentially we're flipping the equation, and we then put the stuff that's on the left hand side on the right of the full equation, so then it's like this, AQ plus 2E minus. Right, and now of course what we can do is we can tidy this up a little bit. We've got 2 electrons on both sides, which is great because it means it's balanced, but obviously they will cancel each other, and so therefore we can end up with our final full equation, which is 2H plus AQ plus zinc solid goes to hydrogen gas plus aqueous dispersion of zinc, aqueous solution of zinc ions. Okay, so that's pretty straightforward for this example, and we're going to go and talk a bit more about more complicated examples in a minute where we actually need to balance things. Okay, so we've done the sort of simple example where we kind of knew what the answer was already, and also we had half equations to start off with, which were balanced, and actually when we put them together, it was already balanced anyway. Now we need to think about the more complicated example, and this is the sort of situation where you start with two redox couples like this. Yep, so this would be 1 and 2. And we need to work out first what the full half reaction is before we can then balance those half reactions and then balance them in a full equation. Okay, and so this here shows us the sort of stepwise process for doing that. So it starts by getting balanced half reactions from our redox couples, and then finally we will essentially put the equations together once we've balanced the number of electrons in both equations. Okay, so that's the sort of summary of the process, but nevertheless we can go through this, and I'll go through an example on the next slide so this will make more sense. Okay, anyway, the first thing we do is we write out the unbalanced half reactions for the two species as reduction. So you're essentially going to write out ox goes to red. Yeah. Then what you're going to do is any elements, so this would typically be the elements that are actually part of the oxidized and reduced species. So for example, if you've got a metal, an example for our zinc would be, on the one side you've got zinc 2 plus, and on the other side you've got zinc. Now this is fine, it's balanced, isn't it? Yeah. But if, for example, we had some other spectator ions in here or some other ions in there, then you might find you're not balanced. You might need to add some more on the other side, and we'll see examples of this coming up. Okay, you've then got to balance any oxygen. Now obviously for the zinc example we don't have any, but the example I'm going to show you on the next slide we definitely do, and the way you balance oxygen is by adding water to the other side of the arrow. Okay, wherever it isn't currently. Okay, then we have a situation where if you've got acidic situation or acidic solution, in that case you can balance your hydrogen atoms that are on one side. So obviously if you've had to add some water, you'll get some hydrogen from that. So you have to add hydrogen into the other side, and so the side where the water isn't has to get hydrogen in the form of H+. Note this is H+, not H3O+. So we're not doing acid-base chemistry anymore, we're doing redox. Okay. But if we're under basic conditions, we balance the H by essentially adding OH minus. Okay, so that kind of makes sense. If you've got an acidic solution, you've got plenty of H plus kicking around, so you can use that quite readily. And likewise, if it's basic, you've got a lot of hydroxide ions, and so there's plenty of that around. So this is the logic behind why you can do it that way. But nevertheless, you've got to remember you've got to do it, and it does depend on the conditions. Okay. Next thing is we've got to balance the charge by adding electrons to the oxidized side, of course, to the ox side. And then finally, what we've got to do is we've got to make sure that both half equations have the same number of electrons together. Okay, so in our hydrogen and zinc example, it was 2 for both of them, so that was fine. But often that won't be the case, and you'll need to multiply either one or both of the equations by a number and multiply it all the way through. In other words, increase the number of species in order to match the numbers of electrons. And again, we'll see that in process on the next slide. Finally, we do what we did before, which is subtract the equations. So it's basically your reduced form and your oxidized form, and then you just cancel anything. And typically that will be the species you're cancelling will be the electrons, but sometimes you end up cancelling waters and H pluses too. Okay, again, there's an example in page 187 of this, and actually on page 188, the example I'm going to show you on the next slide is the self-test from that page. So, that'll be perhaps useful to you. Okay, so let's go through this step by step then in that case, based on the steps that I showed you already. Okay, so we are being asked to use reduction half reactions to write the balanced equation for the oxidization of zinc metal. So that's, Zn, isn't it? By permanganate ions. Okay, we need to know what a permanganate ion is. And, essentially, you can obviously look this up quite readily. And I would, in an exam, I'd give you the formula. But that's a permanganate ion, okay, in acidic solution, okay. So the redox couples here we need to look at are MnO4, Mn2+, And again, I wouldn't expect you to just know that. I'd give you the redox couples in a typical exam or OBA question. But nevertheless, this is just an example, isn't it? This one comes directly from the textbook. Anyway, okay. So let's go through our process. Well, the first thing we had to do is we had to write down unbalanced half equations. So let's start by doing this, okay? So let's start writing this out, and I've actually written this the wrong way around, haven't I? This should be like this, up here, to put it in the correct form. So let's just rub that out, because it's got to be oxidized reduced. Anyway, right, okay. Zn2 plus, and then we'll put an arrow in here. Zn solid, yeah. And of course we can actually, we can balance this really quickly, can't we? Because we know what it's going to look like already. So we'll put in electrons here, and so that one is then balanced. We're done with that one for now. Okay, the manganese one's a bit more complicated. All right, so let's start with our unbalanced equation. Now, obviously, one thing you're going to have to do is determine the oxidation state of manganese in here, and by doing that, you can work out which the oxidized and which the reduced form is. But I'm not going to cover that right now. I'll let you do that yourselves. Hopefully, you've had some practice doing that by now. Okay, but anyway, the unbalanced equation, which I'm going to leave some gaps in to show that it's unbalanced, is this, isn't it? Now, what we need to do, we need to balance the number of oxygens using H2O. Okay, now of course we've got oxygens on the left hand side already, so let's put some oxygens on the right hand side. I'll keep everything else in the same place for now. We may need to make that gap bigger in a minute. So H2O, we'll need 4 of those, don't we? Because we need 4 oxygens. So it's 4, oh, what am I doing? 2, 4, 4 H2O, and of course that's a liquid. Yeah, so we've done that. Now we've obviously got some hydrogens, 8 of them on that side that are not on the left hand side, so we're going to have to put those in. So that's MnO4 minus AQ plus 8H plus goes to Mn2 plus 4H2O liquid, right? And finally, we've got charge on the left hand side and we've got charge on the right. So here we've got on the left hand side we've got 8 plus minus 1, so that's 7 plus on the left, and we've got 2 plus on the right. Okay, so in that case we're going to have to add 5 electrons to the left hand side to balance this charge, and that also works because you can kind of see, if you work this out, that the manganese is in oxidation state plus 7 here. So plus 7 goes down to 2 plus, plus 7 goes down to plus 2, is the change in 5 electrons. So that makes sense too. So it's always a good idea to double check these things. So MnO4 minus AQ, oh, I missed my AQ on my H plus, plus 8H plus AQ plus 5E minus goes to Mn2 plus 4H2O liquid. And again, we've got state symbols for everything apart from the electrons. Okay, right. So that's this one is now fully balanced. So I'll give that a little tick there. But there's a problem because we've got 5 electrons here and 2 electrons here. So we can't just put these together in a straightforward way. We can't just literally write zinc on this side, in order to balance it, because we'll end up with an unequal amount of electrons on each side. Okay, so what we need to do is we need to come up with a solution to that, and I prefer solutions that don't involve halves in them. So the best way to do this is multiply the manganese equation by 2 and the zinc equation by 5, and we'll end up essentially with the following. Okay, and we'll have to use every single bit of space on the slide to write this out. Okay, so anyway, we multiply that one by 5 and we're going to end up with 5 zinc solids plus 2 MnO4 minus plus 16, because it's multiplied by 2, yeah? AQ plus 10 electrons goes to 2 Mn2 plus AQ plus 8 H2O liquid plus 5 zinc 2 plus and then plus 10 E minus. And of course our 10 electrons on both sides are going to cancel, giving us our full reaction equation as asked for in the question. Okay, so I need you to be able to do this, and I will give you some practice in doing this in the quizzes and also as part of the workshop, which is coming in week 7. But otherwise, thank you for listening.